One. Hi everyone, my name is CMAC and welcome to the ACigs webinar series. Today we're having our webinar 22. Today is 6th of July 2021 and you are watching us doing a webinar for Australian chapter of the International Geosynthetic Society. As you know, the IGS is the global society and ACigs is the Australasian chapter. We basically cover Australia, New Zealand, and the Pacific Islands, and we are one of the more than 45 chapters of the IGS. So IGS website is geosyntheticsociety.org, and as you can see in the picture, that's how the website looks like, and you can become a member of the Australian chapter and automatically become a member of IGS. A very great news is that our new website has now been launched. So this picture here shows you what it looks like. We have had almost around 6 months of work into this new website with our developers. And a lot of effort from all of the ACigs team. So I want to acknowledge all of the efforts that the ACigs team has put in to developing this new website. I think it's a great website, but we are sort of open for any comments from our members. I think, we try to put like more useful links on the first page, so you can go to the membership tab, go to the events tab, use the resources. All of our news is up there, also the upcoming events. So as you can see down on the bottom left hand side, we have the July webinar, and then as you go to the right hand side, we have all of the next webinars and the events that we have. So it's a great achievement for the ACigs team, and I'm encouraging everyone to have a look at the new website and let us know what you think about it. Also, as a very important part of our webinar library, so as you can see in this picture, we have basically make available to our members the recording of all of our webinars and events. At the end of this webinar, if you want to receive a certificate of attendance, you can email info@acigs.org and we can organize that for you. And today's webinar, so we thank our sponsors for this event. Solmax is the sponsor of this event. We thank Solmax for their support of the webinar series and support of the ACigs. They are also one of our company members. So thanks to Solmax for sponsoring this event. And the topic that we discussed today is pit thermal energy storage, a sustainable energy resource with geosynthetic solutions, presented by Catrin Tarnowski. So Catrin will talk about this topic for us today. Just a brief about Catrin's bio. So I just have to move the videos to the side. So Catrin is the Senior Technical Manager, EMEA, at Solmax Geosynthetics, providing technical support and engineering advice to engineers, consultants, customers, testing laboratories, and authorities. Prior to joining Solmax, Catrin has more than 10 years of working experience in a third-party inspection and testing laboratory for construction and geosynthetic engineering in Germany, responsible for managing and testing test reports, accreditation of the laboratory, and site inspections. 18 years in GSE lining technology for EMEA region, and now Solmax Geosynthetics, serving for different positions and responsibilities in the company. Catrin is currently working out of Solmax office in Hamburg, Germany. Catrin is an active member of DIN, CEN, ISO, DVS, ASTM, leader of sub-working group in CEN, and member of IGS and GSI. Catrin has also published numerous technical papers and presentations in various international and regional conferences and seminars in the past 20 years. So with that, I finished the intro, stop sharing from my end, and we go direct to Catrin, please, for your presentation.
Thank you, Siamak, for the nice introduction. So, can you see my screen correctly now?
Yes, just before you start, Catrin, I also introduced the panel today. So all of us will be available at the end of this webinar for any questions. So please, if you have any questions during the webinar, during the presentation, type them in the Q&A tab. Please use Q&A tab and use your name as well. So if we don't get to the question at the end, because we might run out of time, we still have your name so we can come back to you with the answer to your question. And the panel today is Su Jong Ho from Solmax. He's joining us from Malaysia today. And Thomas Labda. I think, Thomas, you are also in Germany. Okay, great. So, yeah, floor is yours, Catrin.
Thank you, Siamak. Good afternoon and good morning to everyone here in the session. I will talk today about sustainable and cost-effective thermal energy storage using geosynthetics. What is the motivation behind this presentation and behind our strategy here? Just recently, this graph was published by the Global Monitoring Laboratory, which shows the increase in CO2 output into the world, and it's showing it for 10 years now. And you can see that there is still increasing CO2 output, even if we are already starting to think about to change our way of living, but we have still more output. So there is no planet B, and every one of us should think about what we do. No one from us wants to live on the moon, maybe, or if there is any other life possible on other planets, we don't know. So we have to do something about our environment for our children and our grandchildren. The motivate, The energy transition is focusing on 3 sectors, and we are discussing most recently a lot about the electricity change. We are talking about transport, but somehow heating and cooling is not that dominantly discussed, but it takes in Europe about 47% of the energy demand. So in principle, double of the other both. The numbers in Australia might be comparable, but I don't know it. So today, we have a lot of coal-fired power stations, and we have to change from fossil fuels to renewable and climate-friendly energies in order to overcome the CO2 increase. This means that we have to have a turnaround also in the heat sector, and those we have to use energy occurring and not just to release it into the environment. So there is a lot of energy which we just do not use right now, but we have to. So energy can be used for heat generation, and it can be used for cooling purposes. And the power supply network for this is already growing. It has to grow faster, that's for sure. And but another one which is needed here for is that the energy storage has to grow. So right now we are a lot of focusing on installing new renewable energies, but we have to think about to have a possibility to store all that energy. And heat storage is one of the elements in it. This one is taken from Wikipedia, and it shows what thermal energy storage is about. It said it's achieved with widely different technologies, Depending on the specific technology, it allows excess thermal energy to be stored and used hours, days, months later at scales ranging from the individual process, building, multi-user building, district, town, or even region. ACigs examples are the balancing of energy demand between daytime and nighttime, which we know for long, or storing summer heat for winter heating or winter cold for summer air conditioning, like seasonal thermal energy storage. So which possibilities do we have to store energy? It is known that there is tank thermal energy storage, TTES, which is using steel tanks which are insulated. The pit thermal energy storage is also insulated storage places now. And then we have the natural energy, which is used with the borehole thermal energy storage technology or aquifer thermal energy storage, where the water which is naturally occurring is used. Those last two cannot be insulated, and you can already see that the energy storage capacity is comparable lower to the both upper ones, where we have energies about 60 to 80 kilowatt hours per cubic meter. So the more favorable storage possibilities are the both above. However, looking to those reference projects here, what we can say, the lowest storage volume has almost principally the highest investment cost, and therefore tank thermal energy storage is a very expensive way to store energy. The profitability rises generally with the increasing storage size, which is now possible with using geosynthetics. We are talking nowadays about a volume of 200,000 cubic meter, which is the largest project at the moment which is operating. But larger projects are already planned and in process. What we have to say, if we look to the investment cost and to the economy, is that all the system components have to be adjusted to each other in order to work sufficiently. So I will talk now about the energy transition using geosynthetics, and those brings me to the pit thermal energy storage applications. What is pit thermal energy storage? It began almost 30 years ago, and it was a parallel development, I would say, in Germany and also in Denmark. The objective at that time was to utilize heat storage systems to increase the solar share of solar thermal district heating. But today's goal is to establish large and efficient seasonal or multifunctional storage systems as economical as possible. As I said already, heat storage systems were developed in different variants. Over 30 years ago now, we can see here 4 projects in Germany, one in Steinfurt, which was rather small. We are only talking about 1,500 cubic meters. The Augsburg one was slightly larger, and the other both are still small. So, but that was the first application of pit storage projects in Germany. And different types of geosynthetics were used to that time already, HDPE geomembranes, polypropylene types, but also different insulation materials here in the water. The storage media was always gravel water. But what was the biggest challenge for those projects? Yeah, it was to find the suitable lining and insulation materials, and it was never an experience that it was a very cost-effective solution to that time. But we are now some years in progress, and there are other technologies and other products available. In the following slides, I will present the basic structure of the PTES, the principle and the design. There will be a focus on the sealing system with the geosynthetics, and I will talk about the particular challenges for the sealing products and their installation. So what is a PTES? It is a seasonal or multifunctional heat storage system, and it's a big water battery in principle. Seasonal means that we have one loading and unloading per season, and multifunctional means that there are multiple loadings and unloadings per one season. As I said already at the beginning, the loading comes from different energy sources like renewable, solar, thermal energy, or even industrial waste heat, or we can have combined heat power plants, for example. The construction is done with geosynthetics. This slide shows the general principle of such a pit thermal energy storage place. It is a closed system. The water contained in the pit is separated from the generator, and it is also separated from the user side. The heat exchangers either feed this pit or extract the thermal energy and transfer it here to district heating places. The in and outlet structure consists of at least 2 pipes and with diffusers at the end. Those diffusers serve reducing the flow speed during filling and emptying in order to prevent the mixing of the thermal layering of the water. So they are generally installed in different heights of this pit. What are the necessary design considerations in such an application? We need at first a sufficient size of that location. So it's not a small application anymore, and it needs to be considered considering the environment. It shall be as close as possible to the heat generators and to the consumer in order to do not lose energy over the transport area. The soil conditions need to be considered carefully. They need to be capable of absorbing all the design loads, and they should allow to construct steep slopes. The groundwater situation has to be considered carefully. We don't want to have heat loss because of flowing groundwater here. A typical shape of this pit is a truncated cone, and it shall allow to have a lowest low top surface in order to minimize the heat loss. And on top of this surface, there's always an insulated floating cover, which allows to keep the energy into the application. This shows such a typical pond. This is the 200,000 cubic meter pond in Denmark, and you can see it takes some area. You can see all these solar collectors around, and then the storage application. Now here without the floating cover, and you can see the diffusers on this area here. The system principle, I have here now the pit structure. It's relatively simple, as we can see, and the pit structure is not built with any insulating material at current time, because that would be additional cost to the project, and it is considered that the soil on its own will be okay to store the energy in it. The pond lining, as I said, is relatively simple, but the subsoil conditions have to be considered. So the choice of the correct protection layer, which can be different geosynthetics. The pond bottom liner system has to take lower temperature than the pond slopes here, as the water temperature is layered. But on the upper slopes, there's already high temperatures affecting the liner material. The new materials which are available right now allow such pits to be constructed. So which geosynthetics go into such a pit structure? Geocomposites can be protection layers, which can be geocomposites, but can also be geotextiles only. The protection function is, as I said, based on the subsoil conditions, and stabilization layers might be required. The geomembrane, which is used in such a storage application, has to be high temperature resistant. This is a key function of that product. And it has to offer prolonged service life at temperatures which are above 80 degrees. We are talking about 90 degrees in a lot of applications, and 95 degrees is also to be considered. So it needs to offer sufficient resistance against leaching and against oxidation in this case. It has also to provide excellent chemical stability at such elevated temperatures, because there are chemicals used for this water which is stored in it. What is to be considered is that the material has to offer flexibility at low temperatures, because also low temperatures can occur during the filling stage, but also if it is a seasonal heat storage application, this is to be considered. But on the other hand, it has to offer excellent strength at elevated temperatures. So both things have to be addressed. And thus the material has to provide a functionality over a wide temperature window. And what is need to be considered in addition is the thermal elongation behavior of the material, and that waves could be created, and that possible bridges could occur in the worst case. Thus, the material has to offer stress crack resistance over a wide temperature window as well. Not to forget about the weldability of such material and the long-term performance of the welds in addition. So that is very relevant, and therefore materials have to be adjusted for it. Coming to the floating cover structure, it looks a little bit different because we have now all the insulation layers. We have a heat-resistant geomembrane on top of the water. Then we have different insulation layers on top of it. And we can have these layers are encapsulated by a geomembrane on top. There are new design approaches where there is on top of that, you can also have soil materials in addition. If the geomembrane is exposed, it can be a colored one, for example. The most critical part in this design is most probably the geomembrane, which is on top of the hot water, because this is influenced by the hot water, so it's most affected. And what is to be considered is that the installation is sufficient thick to cope with all the heat occurring in this application. Which geosynthetics are used in this floating cover? So there is the floating cover liner, and as said, this floating cover liner has to be high temperature resistant. It has to cope with the design load of the upper structure. It has to cope with water vapor, and the water vapor transmittance of that layer should be very low in order to keep the insulation as dry as possible. So there is water going through that material. There are different geocomposites, stabilization or separation layers between the insulation layers. They need also to be addressed to be sufficient heat stable. And the exposed upper geomembrane has to offer, if it's exposed, sufficient UV resistance. It shall have a low thermal elongation, so in order to reduce waviness. And therefore, it is also recommended to use a light-colored geomembrane, because that reduces the heat on the liner, which reduces the waviness as well. And it can be colored to fit into the environment. So wherever it is located, a color can be chosen. The floating cover insulation layers, there are different possibilities available nowadays, and there is still progress also in this materials. The insulation layers which were built now used a lot of foam, and they also use granules, which are here in this case so-called lacquer boards, which you know from plant growing applications. So those are materials which are used, but there is further development into it. And it is to be addressed that those have to be heat resistant as well. And it has to be addressed that water which is occurring because it's diffusing through the lower layer must be extracted from that layers. So the installation layers have to cope with the water which is entering, and it needs to allow to extract it again. So what are the challenges now for the products, specifically for the geomembrane? And we know all that HDPE geomembranes, which have been used, and they have also been used in that applications, the highest temperature recommended for such geomembrane was in principle the long-term temperature below 60 degrees C. And as you can see in the table from George Kerner, the lifetime prediction of geomembranes at 40 degrees C is a total prediction of 69 years, which tells us at 60 degrees we are already below 20 years. So this is not sufficient for applications where we now consider 80 degrees or even more. So there is a limit in that product. But the industry is not sleeping, and there is further progressing in developing high temperature resistant geomembranes. And there are different types available now. And the polyethylene industry had developed tailored comonomer and tailored polyethylene types for high temperature applications. And this is coming from the heating sector. And those polyethylene types have tailored comonomer and molecular weight distribution for unique structural property balance. They're offering a good processability, good heat seal properties, and mechanical strength, toughness, tear, and stress crack resistance. They have been evaluated in different testing procedures, as there are leaching procedures, chemical immersion tests, and so such tests are covered in EN and ISO norms. The suppliers have tested their materials in hoop stress performance tests according to ISO 9018, which is also considering different chemical conditions. For the geomembrane applications, we do not have to forget about the dimensional stability. We have always to evaluate, because this is a key performance of that applications here, because we want to reduce, we want to have the utmost laying flat for such applications. What you can see in the pictures here is typical autoclave procedures. One is from Denmark, which has air insertion on the one side and water insertion on the other side. And the other one is insertion in the fluid in higher temperatures and into higher pressure. The evaluation of the lifetime can be made based on the temperature profile in the storage application, and typically more than 20 years are requested. We are talking nowadays even about 30 years, but this is still a challenging lifetime depending on the temperature requirements, which are now asked to be established. Another challenge which is to be addressed is the water filling of these applications. The water has to be clean. This is essential for the functionality. There shall be no change in the water quality, so it has to be covered during the filling stage. There's a chemical introduced to reduce the microorganism and to reduce the oxygen content. However, what is to be addressed is that the oxygen content in the water is reduced with the rising temperature, and it's also reduced with these chemical, which is it's in principle a salt. The challenges to the insulation layers, as addressed already earlier, is they have to minimize the heat loss to the atmosphere. So they have to be sufficient thick, they have to be sufficient distributed over the whole floating cover, and they have to cope with all the heat occurring in it. And for sure, there is water vapor created, and it has to be managed that the insulation is dry. And here you can see that with the rising temperature, there is already a high water vapor transmittance through a through the specific high temperature liner. So at 90 degree, we talk about 2.6 gram or even higher content of water diffusing through the liner on 1 cubic meter per day. So the insulation layer has to cope with it. On the other hand, we have to consider the oxygen which is created. And as I told, the oxygen which is created in the, which is filled with the water into the pond, while introducing the chemical and while heating up the water, this oxygen is going to the surface of the water, so it's accumulating below the floating cover. So this has to, and the oxygen has to be driven out of the application. And we do not want to have that oxygen into the water, because it will have corrosion of the steel elements like the diffuser towers or the pipe which are in this application. The good thing with it is if the oxygen is released from the application, it is also helping to enhance the service life of the geomembrane in it. So which control and service elements are used on such a floating cover? Yes, we have the ventilation layer, ventilation buildings to keep the insulation dry, and we have to address exhaust outlets to get rid of the oxygen which is accumulating below the floating covers. And what is typically needed on every floating cover is the shafts, inspection shafts, to control the whole application. This is a standard for any floating cover, and one of these inspection shafts is typically located above the diffuser tower. We have to address the water management on top of this floating cover, which is critical here in order to have always stable insulation, insulation layer thickness. So water shall not be accumulate on top of it, because it would have an effect on the effectiveness of the installation. The second part of this installation will now focus on the installation of the pit thermal energy storage. And you can see on this picture the floating cover procedures. There is the lower liner, which you can see, and already some of the protection and separation layers on top of it. What is to be considered during the installation? It is always the high temperature and the temperature differences. It's not only the high temperatures, we have always to address that we have varying temperatures, and those we shall focus on achieving the best laying flat of the whole application. So therefore it is relevant to have the best weld quality achieved, and to address that the lowest amount of extrusion welds should be executed. The weld rod should have the identical formulation as the geomembrane layer, and we strongly recommend that T-joints are constructed using double hot wedge welding and not to use the typical extrusion welding procedure. This is by far bringing a lot of advantage into the application. The geomembrane of the whole application should allow for the lowest amount of weld with the focus of double hot wedge weld and the lowest amount of any extrusion weld. And the German DVS guidelines give a good overview about how such things could be executed. So if we are installing such an application, we are following strictly DVS 22225-4, which is the guideline for landfill lining in Germany, but it's also applicable for PTES. It is to be addressed that the thickness reduction in the seam area needs to be controlled. The amount of squeeze out needs to be controlled in order to do not have the effect of a lot of squeeze out, which is then at the end acting as a notch into a geomembrane, for example, which is a critical area considering high heat or considering temperature changes. And for the extrusion wells, it's to be considered that the grinding shall not occur outside of the seam area. That should be kept to a minimum, because we have to consider what we have higher stresses in such an application. And relevant here is also to execute the connection to penetrations with a lot of care. So the PTS installation begins with the prefabrication of penetration, of shafts, of vents, of pump sumps, and is always to address the high temperature exposure of such elements. So the right raw material has to be chosen, and the execution of the wells has to be done with utmost care here. This picture shows the installation on the slope, and as addressed at the beginning, the protection layer has to be sufficient to cope with the situation of the subsoil. So there should be not like, I address the cheapest one, and later on I will see, okay, I might have puncturing of my geomembrane, considering that the geomembrane just on top of the slope can be relatively weak at high temperatures. Joints on slopes should be avoided because to address that their lowest amount of joints should be established. So geomembranes could be manufactured on lengths like the slopes. Laying flat, as addressed, is a key in these applications. Here's a further picture showing the start of the installation of that big project with the 200,000 cubic meters. And here is further progress in the application. You see the diffuser tower here. The diffuser tower is penetrating the geomembrane, and it needs mechanical fixation at the bottom and also at the slope, because this diffuser tower has some shaking while it is operating. So this is to be addressed during the, it's addressed in the construction, and there is some technology behind to do this, which is not highlighted here in this presentation. Concrete protection liner elements can be used on the slope fixation. Here's another picture which shows good laying flat characteristics, and it's only shown to rest. You can see it's worse weather conditions here, but it's to be addressed that laying flat is a key element of a successful application here. Thus, I would like to show this picture, which shows how wells could be executed. The left side picture shows that there is a flap installed at the length at the geomembrane, which is helping to get with the weld device into the weld zone. And while the thickness reduction of the seam cannot be controlled in the flap, it's already a controlled thickness reduction when the weld device is entering this cross-sectional seam here, and thus a good seam quality can be achieved. And the right picture just shows how an extrusion weld should look like in such an application. It should be even, it should have no grinding at the edges, it should have not a lot of excess amount at the outer sides of the seam, and the surface of the seam should be even and leveled. You know the picture from the floating cover installation. This is the lower liner. The installation of these layers typically is done aside from the pond. So in sequences, it is then pulled over the filled pond after the sacrificial layer was removed earlier, which kept the water clean. And during this application or installation of the floating liner panels, it's also to be addressed that the service elements or the structures, outlet structures, have to be constructed aside from the pond already, and it has to be considered that they are set in the right place. This picture shows some typical elements here, the penetrations up to the lower liners. Others are only penetrating the upper liners. And there are the shafts which go down to the lower liner. Then we have the exhaust outlets, which are penetrating also the lower liner. What you can see here is that the ventilation pipe is wrapped in principle in order to have no stress due to this inner pipe, which is moving. And we do not, and the floating cover is moving all the time. So we have to address that penetrations which are going through, that the stresses are not just occurring into that liner connection to that element. Here's a further picture where you can see also the structures which are in the floating cover, which penetrate the lower liner. And this picture shows now the installation of the insulation layers. And as mentioned earlier, there are different insulation technologies available now. Here we have the insulation with the polyethylene foam, together with geonets, what you can see here, which is installed in different layers, sequence in different layers. Another possible installation is showing the installation of lacquer balls here. And the lacquer balls are blown in. And the difficulty with this one is to have a really stable thickness of the installation layers at any place. So there are favorable aspects for foam applications compared to this one. However, sometimes it's each one has a plus or a negative aspect, and there is also further progress ongoing in insulation layers right now. After the installation layers have been installed, upper layer, geomembrane layer is installed, and as you can see here it was a gray geomembrane was chosen in order to fit it into the environment. You can see here the insulation layers below. And a key element of that geomembrane here is that it has to be UV resistant, because this one is an exposed one. And it has to have best dimensional stability in order to allow waviness to be reduced. And therefore, a light color geomembrane is of advantage. And it is also an advantage, as I addressed earlier, to have a geomembrane with an extreme good dimensional stability, which means it has a low shrinkage and it's allowing, therefore, to lay flat. The installation is ongoing with the typical welding procedures here as well. This picture shows greatly how a CO2-free project can be created. It shows the solar panels around the PTES structure. And on the dam of the PTES structure, we have photovoltaic panels, which are producing the energy for the operations building. And the operations building is located here in the dam. And this is taking the energy from the PV panels. And you see the light color geomembrane, so the insulated floating cover on top of it. And this illustrates greatly what we can do for our environment in the future using the modern technologies which are available now and the products which allow to do such projects. So what are the advantages now which are created by pit thermal energy storages? Compared to the tank thermal energy storage, which were the development at the beginning and which are still also be built, it's the high storage volumes which can be realized now, and which makes it favorable in respects to economy. So we have a high degree of efficiency, and such big storage applications can be combined with already existing systems. So it's just like the systems are there, but we had no possibility to store all that energy right now. So we have now an increasing flexibility of the supply sources, and thus we can secure the supply of energy more safe as we could do in the past. So with that, we have a stabilization and an assurance of the heat price or the cooling price, for example. So we have a cost-effective construction possibility and are securing energy. We are securing cost-effective energy with it. Fast, we have with these pit thermal energy storages, we have a fast implementation of the energy transition. So we are doing something for the environment, particularly in the heating sector. This is necessary, and heat storages are a key factor for a successful heat transition here. The pit thermal energy storages with temperature-resistant geomembranes enable a competitive and cost-effective and a long service life solution, and they guarantee the security of energy supply. So we have an efficient and economical use of innovative sealing products and a practical, simple system configuration. And this is what PTES are. And they allow for the future to save, to support the CO2 reduction for our future environments, for future generations. And we as Solmax are doing something about it. We are proud to do it. And we say, even as humanity strives to advance, it is destroying the most precious natural resource that it has, the Earth itself. And we have to do something about it, and we all can do it together. Thanks for your attention, and we welcome questions. We as a company are supplying and installing on projects, PTS projects now for over 10 years, and we are happy to answer your questions. So feel free to address the questions right now and questions after the session of my colleague, and questions which cannot be answered now, we will answer later. Thank you.
All right, great. Thank you, Catrin. That was a very interesting presentation. So I think without wasting any time, we just go to Sue and his presentation on behalf of Solmax, and then we open for the questions and answers. Sue?
Thanks, Evan. Let me set it up. Okay, hope my screen is showing up. I'll present a quick and short case study for PTS here in Asia Pacific. We have a PTS being constructed back in, I think, almost 2 years now in Langkawi in Tibetan Plateau. It is located around 4,600 meters above sea level and constructed around April 2018. And the whole system is operational since December same year. So it has been operational for somewhere around 2 years, more than 2 years now. So this PTS project in China, in Tibet, it's the first large solar thermal heating systems in Tibet. It supplies to more than 90% of the Langkawi town heating demand with clean energy. So I would assume this is also the first large PTS project we have here in the Asia Pacific. The whole project is designed, planned, and also developed by a Chinese and Danish JV. So the next slides here, we have a schematic diagram on the left side showing how the system actually works. So PTS systems helps ensure on-demand heat supplies during peak period. For example, during winter time, when there is a limited energy generation from the sun or any other renewable energy sources. During summertime, the excess solar heat produced by solar heating plant is stored within the PTS. So the excess heat warms up the water to about 80 to 90 degrees, like Catrin mentioned before, before it might be even higher. So in the winter time, when the district heating demands increase and exceed the solar heat produced, hot water from the storage is actually withdrawn and go into the systems. So it's actually a mutual systems where during winter time, we are extracting energy, but during summertime, we are storing excess energy. For the materials used for the project, we have a protection geocomposite at the base of the storage pit. And we have the high temperature 2.5 millimeters materials being used as the main geomembrane containment for the PTS storage, where it is manufactured and formulated to resist high temperature. So we also have a geocomposite on top, especially on the cover lids, and also sacrificial layer, and the final cover, which is another layer of geomembrane, but it is with a much lighter cover to actually reduce thermal expansion, for example, wrinkles, to promote lay flat. So in the PTS as a whole, we actually have a few layers of geocomposite and also a few layers of membrane inside. So this is a pictures on the base of the PTS storage, where you can see here the high temperature geomembrane is being laid, and there is a temporary ramp on the left side to allow any construction, for example, for the diffuser in the middle to be constructed without damaging the lining systems. And this is a picture where you see the water has been filled, the sacrificial layer has been removed as well, and the high temperature geomembrane on top is being pulled to actually covers the storage pit. And lastly, I have one picture that shows the overall project for Langkawi PTS. So the pit on the background, which is on the far top of the pictures, you see a little squares inside the pictures. That is where the PTS is. It is very near to the solar farms or solar panels, so that we can actually reduce any heat, losing any heat during the transportations. So that's a quick summary or short case study that I have. And just to introduce ourselves, Solmax, it's almost 40 years now in the industry. We are one of the leading geosynthetics manufacturers worldwide, with around 10 manufacturing plants in the globe. And whereas for Solmax in Asia Pacific, we have 3 manufacturing plants, one in Malaysia, one in Thailand, and another one in China. Whereas for offices, similarly, we have one in Shanghai, China, we have one in Bangkok, Thailand, another one sharing the same manufacturing facilities location in Malaysia. And we shouldn't forget as well, we also have an office here in Sydney, Australia. So Andrew Christophely, or Andy, normally that's how I call him. So he is the country sales manager for Australia. So his contact is written on the slides, as well as myself. I am the technical support and also to support on specification for any material. So if you have any questions on the systems or on any other projects, I mean, feel free to contact any of us. Thank you. Passing back to you, Semak.
Thank you, Sue. All right, so we have around 5 minutes for a few questions. So I go straight into the questions asked by our audience. So one question here is from Thomas Rigler. Are movements of the floating cover due to water level fluctuations a challenge for the geosynthetics?
There is in principle no water level fluctuation here. This is, as I said, a filled pond, which is not emptied. So it's just a heat exchange. So there is no problem with the water level.
Yeah. The next one, is this PTES presentation available in the Solmax website after this presentation? So I can talk on behalf of ACigs. We do record the presentation. We make it available on ACigs website, but I'm not sure if they're asking for the actual presentation slides, Catrin?
I would assume that we would make it available for some of the people who are listening.
Okay.
Just
Perfect.
we will, and then we can.
Then the question also from Su Han Wong. Do you happen to have a carbon footprint result when these geomembranes are used?
That is something we are starting right now. It's not only the geomembrane use, it's the full application. So this needs also to address the full system component, but it will definitely be made. So yeah, it's not now available, but there is progress in it.
Okay. Yeah, and I assume there's a list of things that you guys need to go through, basically calculate the carbon footprint for every little bit of the system, and then add them up together. One question I had about the maintenance of the system after the construction is finished and you are in operation phase. Compared to like other available systems, what are the maintenance differences and maybe the cost for the maintenance, how it's compared to the other systems?
Thomas?
Yeah, the main challenge maybe for the PTS systems is to collect all the maintenance. Directly you have less maintenance, but the challenge currently is more how to collect the rainwater of the PTS cover. So it's one of the I would say currently main maintenance cost which you have with the system. Other costs are what Catrin mentioned in her presentation is yes, to avoid oxygen in the water. That is something that you have to consider, and maybe you have to, if you have too many oxygen in the water, then you have to use some chemicals to add that some not direct main costs, but some additional costs for the system. And furthermore, I cannot add some costs currently. Yeah.
Okay. Then with regards to the lifetime of the system, Catrin mentioned in the presentation that it's a long life system. So what sort of numbers are we talking about? And you know, again, if we have any comparison with similar systems that we can say this actually lasts longer than the rest of the systems.
As mentioned, it starts with, in principle, nobody is talking about lifetime below 20 years. It's exceeding the 20 years, it's going up to 30 years. 30 years, everyone knows that there is a limit on geosynthetics with regard to heat. So it's now the economical aspect in it. It depends on, it's a balance between the enduring long-term temperature, which could be maybe 80 degrees, but might rise up to 95 degrees. And this has to be balanced. Typically, yes, as I said, it starts with 20 years would be the lowest amount, but we see a lot of requests where it's written 30 years service lifetime of such an application. But okay, this is not like a landfill, for example, where we know after that 50 years, or we will have another 50 years. If we talk about such applications, we know we come to an end of life of the product because they are strongly aged during their service life.
Okay.
Yeah.
And lastly, about decommissioning. So I'm not sure around the world, like what is probably the oldest PTES system that exists at the moment, and is that getting closer to like end of life, and the decommissioning has started to be planned maybe? So if you can maybe elaborate on how the system can be decommissioned, is it just releasing the water and just basically taking off all of the geosynthetic components?
Might be treated. So there is, I don't know if these small applications, which are trial applications, there is not a big deal in looking to a project with 1,500 cubic meters to deal with it. But for the other project, this has to be addressed by because the water which is in the storage application is not just a clean water. It's a water where a chemical was introduced, so it has to be addressed that this water might be cleaned. And the geosynthetics used are, they can be treated as in other projects. Will come more and more now that we have to think about to reuse the geosynthetics, maybe for waste, for heat generation, for example, or they might have a stage where they can be introduced in a second product cycle for something not very relevant, but that needs to be addressed. So right now, the larger project, none of them is in decommissioning. They are all in that is something new. This industry has to work on, and we have to face this problem as well. And it's already addressed in specification that recycling is a topic.
Okay, perfect. Last question, I have one here from John Cowland, my good friend. He's asking, how long does the heat remain in the pit? How quickly does it dissipate?
Thomas?
Yeah, if we talk about a heat loss, you talk about 1 to 2 Kelvin per month, but it decreases. But it's depend from every project. It depends on the insulation, what Catrin you use. It depends of the thickness of the insulation. So every project of this is a unique project, maybe to say. It's all the system that you have to consider, how the efficiency of the pit, where the heat comes from, the sources, and so on. So also about the lifetime, which we mentioned before, you have to check every project to look into the details, and then you get more or less to say the full picture of it. Yeah, so it's every project is different. Okay. Every pit.
Great. Thanks very much again. So thank you, Catrin, for the great presentation. Sue, for the nice pictures and the case study you presented as well, and Thomas for being on the panel today. Thank you to our audience who stayed with us until the end. So I think this is the end of our webinar today. We wrap it up here, and our next one is going to be in August. So again, I encourage you to definitely check out our new website. www.acigs.org is the address. And let us know what you think about the new website. What else do you think it can be included on the website? And definitely check out the future events. Thank you again, and we will see you in our next webinar. Thank you. Bye.
Thank you so much.
Bye.
Thank you all.